So let's start this session. We have basically 3 talks. First is Sanjay about India-CMS collaboration. They are doing it from there. I'll give you warning after 5 minutes.
Can you hear me in the back? Okay, thank you. So I have to move this one because I'm lefty, so it's very hard for me to find. So I'll be basically talking about the Indian contribution to CMS. So I'm not going to start talking about all the contribution we have made since beginning. So basically focus on few physics results starting in the round 2. These are the recent results. And then I'll just basically discuss about some of the hardware upgrade we have been participating. Now, a little bit about the CMS, how big the India-CMS collaboration is. This is the CMS collaboration, about 6,000 people. We are about 160 participants in CMS, and there is about 247 institutes, and we have around 14 institutes from India, out of which 4 are Dighe institutes and the rest are DST institutes. Now, the CMS has made enormous progress in getting lots of data, about 211 inverse one data. This is combined one since 2010. And these are the splitting year-wise. And the peak luminosity has increased twice as the designed luminosity. And as we get the luminosity or beam intensity gets higher and higher, the number of interactions or proton-proton collision or bonds crossing gets increases. And that puts a lot of challenge in the detector hardware. And I will just come back to it later. And now we are collecting data with 13.6 TeV center of mass energy. Now, what kind of, so we have about 1,170 papers, and about 10% of that papers have Indian participations, not like only Indians have worked. It's an Indian collaboration along with other people, they have participated. There are some papers only Indian groups have already contributed. And that constitute different areas. We have different physics groups. And for example, CMS physics program has Higgs, the vector bosons and top quark beam agents, and other exotics, and so on. And that contains a lot of different sub-sections of the physics, the detailed physics studies. And the India-CMS collaboration participates almost everything, including even heavy ion physics. We do take heavy ion data, which I'll come back later and show 1 or 2 results from there. Now coming back to, I will show you few from each, because as I said, 10% of the papers is too much. I'll show you some of the recent papers using the round 2 data. and only got 5, 7, or 10 of them, and very briefly go through them. And these are, I haven't put the names, but these are the papers which have only contributed by Indian groups. First, starting with the Higgs boson, we started with still searching mode in early 2012 to observation in middle 2012. And over the time, we have made enormous progress in Higgs, studying the properties of the Higgs, including the couplings and couplings to the third generation. And then it's a precision mass measurement, which is almost a factor of 3, 2.5 to 3, since we started 2012. Now, about the specific physics contributions, this is all the results I'll be showing is using the 13 TV data around that is collected during 2016 to 2018, 3 years. And this is Higgs 2 BB and 2 photons, and where one of the Higgs goes to 2 BJs and the other Higgs goes to 2 photons. And that's sensitive to Higgs coupling, self-coupling. And the production mode is basically gluon and HH modes, even though it's much smaller than the GGH mode, the cross sections. And there are parameters, 5 parameters controlling these interactions, and these are the standard model interactions, and there are some parameters which comes from the beyond standard model interactions. And you can see the most of the Higgs, when we do analysis, look at the peak, like you have seen the earlier slide, Higgs to gamma gamma, and you don't see any significant signals in the Higgs mode. And so this is basically one of the 2 photon invariant mass and the 2 jet invariant mass, and you don't see any significant excess compared to the data. And so we put the limit on the cross-section times the branching fraction, and that is about less than 1 femtobarn. And that is still 7 to 8 times larger than the standard model predictions. So we have to wait for the more and more data. The other one is basically TT bar H and TH production in the multi-lepton channels, where the Higgs decays to WW tau tau or GG modes, where the W tau or GG goes to leptonic modes as well as the hadronic tau hadronic modes. Depending on the leptons as well as the number of leptons and number of tau hadrons, you can split the whole topology into 10 subcategories, depending on the number of leptons and hadronic tau decays. And again, the signal region is defined based on the lepton and the hadronic tau multiplicity. And for the TT bar H, we just, this is the signal strength, which is basically the cross section with respect to the standard model. They're very consistent with the standard model. And here is also, you see not much strength for this for these modes. And you can use them. This is basically very one of the main pros for the top UCAO coupling, and you can use them for the finding this top coupling, and that comes out to be either minus 0.9 to minus 0.7 or plus 0.7 to 1.1 at the 95% confidence level. And that's the definition of the, again, UCAO. This is UCAO top coupling with respect to what you observe with respect to the standard model. Coming to, again, this is Higgs to WW, and this is the second largest branching fraction after Higgs to BB. And this is multi-channel modes. And you can see the Higgs going to WW and they decay to leptonic modes. So you can look at either the same flavor or you can look at the opposite flavor modes. And they are produced in different modes like GGH, BBF, or VH, where V is W or Z. And it's very difficult to, it's not difficult, it is not, we do not reconstruct Higgs mass, but we look at the different variables and fit the number of events with respect to the background in your data, in keeping all these 3 different production mode as a floating parameter. And you get, not only that, you can get all the cross sections in different finer phase space that you see in the different PT beams. And so what we show here is the signal strength with respect to in the different production modes. And there again, they're very consistent with the standard model predictions within the error bars, 1 or 2 sigma within the error bars. And you can measure the standard model coupling parameters like KV and the fermion coupling or the vector boson coupling with respect with top quark, with the Higgs boson, and that is consistent with the standard model prediction. And these are some finer grained signal strength using the simplified template cross-section framework, which looks at the cross-section in the different phase space, finer phase space. And Higgs to gamma signal strength, again, you can look at the different productions mode, and again, you simultaneously measure the signal strength in all the 4 signal channels. And the total signal strength comes out to be 1.12, and these are the different production modes. It's a signal strength, and with respect to the standard model as 1. And you see the signal peaks, and there are signals there. And you can again measure the different the cross sections in the different finer phase space beams, and you can go and find all the details, more even finer phase space beams, the signal strength in the paper is mentioned. Okay, so now coming to so there are plenty of Higgs. I just showed 3-4 of them, but there are a lot more Higgs analysis works going on by India-CMS collaborations. Now coming to one results that Indian group has contributed is a BS to mu, which is basically goes through the loop diagram, and any new physics in the loop can change the observables, whether it's a lifetime or branching fraction. And the BD is much more even suppressed with respect to BS because of the CKM suppression. And theoretically, it's a very nice model, both theoretically and experimentally, because it's a much more cleaner. And the branching fraction is, however, very small. So you get about 3 out of a billion BS produced. 3 of them decays to BS, decays to mu, and 1 out of 10 billion goes to B0 to mu. And this has been sourced for the last 40 years, starting in 1984 by Clio, and till in 2015, the CMS observed it with 5 sigma significance. And CMS has published so far about 5 papers on that, and this result is based on the 6th one, which is already public. And so this is basically using the full run-to data, and that's the inherent mass, and that's the decay time. And you get both the lifetime as well as the branching fraction from the 2-dimensional fit to the inherent mass and the decay time. And that's the CMS branching fraction for BS to mu compared to the standard model prediction here. The error bars is still 3 times, standard model prediction is 3 times smaller. And this branching fraction, this errors is mostly dominated by statistics. So we need to wait for a lot more statistics to get down the standard model, to compare the standard model prediction. BS, we don't see any, it's very hard to see BS actually. There is a very tiny peak there. And we don't see any significant signals for the BS. So we put the upper limit on this one, although the standard model prediction is this. The lifetime, again, with respect to the standard model, the lifetime is 1.83 times plus minus 0.23. And this is one of the single best measurement by any individual experiment out of the LHC, CMS, or Atlas, even though there is a combined result existing. Okay, now coming to another one, supersymmetry. There are a lot of groups in Indian collaboration working in the supersymmetry. And I will focus on 2-3 of them. And because I will be showing the similar slides almost all the time, so I want to tell you the general strategy they follow in the supersymmetry, so that when I show the same slides, you know what I am talking about. General strategy is basically, if you have a supersymmetric, in some observable supersymmetry is dominated, just look at the signal dominated region, and we call it the signal region, and where we just blind the data here and wait till last minute. We freeze all the procedures here in the non-signal region, and then after all the background estimation method is validated. We just unblind this data. This is for the one-dimensional distribution, but if you have 2 or 3 or 4-dimensional distribution, we even subdivide the signal region to multiple bins. And there is a control region like this, which is dominated by backgrounds. And we try to use that to estimate our background methods. And we validate it in some validation region, which is disjoint with signal or control region. And once the validation works out, we just look at the signal region and open the data and compare it with the backgrounds. And if the data is, there is enough excess, then we just try to understand that one. If we don't see enough excess, then in the multidimensional space, we just put that some exclusion plot. And that's what I will just go on showing from now on. And that's one of these bins. You can see, I was showing the 3 bins earlier. Over there, like signal region 1, 2, 3 bins, but there are people who use even 200 of the or 200 bins. So one such thing is basically strong production of gluino and quarks and going to the top quarks. And this is the multi-jet. So all the top going to bottom and W going to 2 jets. And so in the final state, we have a bunch of jets and with the missing ET coming from the LSP here. And we have about 174 signal search bins in the 4-dimensional space, and they are the 174 signal search bins. And each bin, you can see the standard model background, which are colored ones with the data points. They are almost very consistent with the background. There is no excess. Those points with excess has very higher statistical error bars. So they are consistent with the standard model backgrounds. So if we don't find any significant excess, you can put the limit and the limit on the gluino as well as stop quarks as well as the lighter quarks comes up to be around 2.3 TeV, and it's about 1.2 TeV, and this is 1.7 TeV, which is basically about 200 to 300 GeV better than the previous results. Similarly, in the other modes of the stop, we have fully hadronic again. The fully hadronic with a better, it's a different, even though it's fully hadronic, it's a different algorithm we use for the top quark and W boson tagging algorithm. And we do not see any excess in these things. And we, again, put the exclusion limit in the stop. In both the scenario of stop minus LSP greater than MW or less than MW. And the gluino mass, again, it's about 2.2 to 2.3 to 2.3 TeV exclusions. This is one of the analysis of the boosted G bosons. That is, I think we have done for the first time in the CMS. And that is when you have gluino going to 2 quarks or low momentum quarks. And so most of the energy is carried by the NLSP. And then with the low mass splitting, and so you get a G boson to be boosted, and you get a very wide cone actually for the boosted G bosons. And again, you look for the 6 search bins in the PT miss regions, and you can see standard model background with respect to signals, with respect to the data, and there is a little bit excess, very small excess with large error bars. And you can see if there would have been at gluino at 1.7 TeV, you would have seen about 10 events there instead of about 1 events there, and there is nothing there. So you put the exclusion limits on that one. And again, this is again, I'll just go on in the top tau decays in the hadronic modes, and we do not see, this is the little bit lesser data. Again, we do not see any excess, and we put this, I'll just go on very quickly. And this is another very exotic resonance looking for the excited quarks and radiating the photon and the jets. And you can look at the photon jet invariant mass. And if you see any peak, then you know that there is there is something there, but we don't see anything. It's the data is very flat and there is no peak. And based on that, you can look at, you can basically put some constraint on the mass of the excited quarks. And the data has gone to of the order of 6 to 6 TeV, 6 to 7.5 TeV. 6 TeV for the excited quarks, and our B star about 2.2 TeV. For a quantum black hole, that's about 7.5 TeV. I think this is done by purely by the Indian groups. And this is multi-lepton channels, and I want to skip it, looking in the three different, interpreted in three different contexts, and we don't see any signals there. And so I just put, they put the upper limits on each of these things. Well, the type 2, type 3 CISA, these are the heavy fermions there, and you see these are the vector-like leptons, and this is the leptoquarks decaying to final standard model particles. We do heavy ion physics. We take about 1 month every year during the runtime heavy ions. And one of the things that we have done looking at the femtoscopy, which is basically looking at if you have basically looking at the particle emitting source region, if you have a particle coming out from the QGP, how big that region is, and that following the femtoscopy tool. And people, for that, you have to look at the same particle emitting from the source. So people do look at the pi or kk. But we have looked at the Kesher, lambda, which are neutral particles, looking at our sensitivity of the detector, CMS detector to these kind of particles. And this is basically the size of the source as you go to the centrality, and that this is a full centrality, and that's the low centrality. When you have full centrality, you get the bigger size of the source. And then you can talk about whether the force between them when they were in the QGP region, if they were attractive or repulsive based on their range, actually the scattering length. Okay, I'll just last 6 minutes, I will talk about detectors. And this is, you have heard from Satyaki, like we need to have with 5 times more the luminosity and with a huge number of pileup, we need to upgrade our detector to keep up with the intense particles coming out. And one of these, so we'll be starting with 2025. It was supposed to be 2025. Now we are moving to 2026 because of the COVID reasons. So now LS shutdown will be 2026 to 2028, 3 years instead of 2.5 years earlier. And the round 4 starts at 2029 instead of 2027. And there are some detector upgrades happened actually since this last shutdown. There's something going on basically in the end of next year. There will be some GEM also, which is the Indian group are participating. They'll be replaced. But major detector upgrade will be happening here in most of the detector upgrades. And what we'll be doing is basically all the left sides is basically replacement of existing system or detector, including the electronics. And these two are basically where will be detector upgrade or replacement, the electronics upgrade or replacement. And the ones that you see in the greens is basically completely new detector that will be installed during the phase 2, which is 2025 onwards. And out of that, I showed that many of these detectors upgrade India-CMS is participating, and one of these basically a level 1 trigger. This is trigger the electronics readout boards, and keeping the bandwidth from 100 to 100 kilohertz to 750 kilohertz, as well as the trigger decision making, which will be increased from 4 microsecond to 13 microsecond, within which the trigger should decide whether to keep that data or not. And not only that, this will accommodate the tracker information now, which will be included in the L1 trigger. And this is basically that this is already fabricated and within Indian companies, and it fabricated and assembled within India. And the other one is a tracker. This is the tracker modules. You see each of them. And now in the phase 2, we'll have a lot more smaller material. You need small material when the tracking particle goes so that they don't get multiple scattering and change their momentum. And you can see this is as a function of radiation length. And these colors basically tells you like say how much before inner tracker, within inner tracker, in between inner tracker, outer tracker, and in the outer tracker. Still, you see very small material, so that gives us much more precise momentum measurements. And we try to build once about 1100 once such small one. So we want to build 1100 of them in India. And this is how it looks like each of them. And if you expand it, these are the each components. You want to put them together, and these two sensors should sit on the top of each other at the micron level precision. And that's what we have built already, one of the dummy modules and one of the functional module that is built in India. And this is very important because of the reagents actually this should be used in the one of the major role for this detector is basically will be used for the L1 track triggering. The second one is basically edge-cal, and basically the process where, for example, if you look at one of the example is BBF and BBH, and then you can see this Higgs going to gamma, this jet and gamma, they can be very close to each other. And with a lot of pile-up environment, you will not be able to see. But this calorimeter has both, not only they are very precise, but it's a timing information is there. If you put some timing cut there, and you can see that actually they are very, you get the very clean jet versus photon separation. And there are two parts. One is basically the electromagnetic calorimeter, and that is CE, and the hadronic calorimeter. They are more radiation prone because it's in the forward direction, and that's the hadronic one, little bit low eta regions. And they will be basically electromagnetic calorimeter will have this calorimeter would have high the silicon sensor based, and this is expanded view. And India is trying to participate on this one. And one of these things is electronics, and you see here, and they are basically again assembled, and they are fabricated within India and tested also. And that is one of the very interesting work we have been trying to do. The other one is a muon upgrade. We have muon has drip tubes as well as RPCs and cathode strip chambers. And here in the end cap regions, we have there the GEM foils, and we have already contributed in the GE21 here. And but there is more in the phase 2. There'll be ME0, which is basically covering to about 3 in the pseudo rapidity regions. And we'll be basically providing the GEM detector on this one. And again, we have been working on this since last few years, and prepared this GEM foils and tested it and assembled it and tested it. This can be used also with different medical imaging purposes. And this is I think let me see. So so this has I believe the GEM is if you have a very you can correct me, but if you have a very high radiation, so GEM is one of the detector that so we have 3 different kind of detectors in different region based on the radiation dose. So if you have a very high radiation dose, there are some detectors you should put in the high radiation dose compatible detectors.
Actually, not only radiation dose, it also depends how fast the detector is. So, for example, GEM and RPC mostly used in trigger much more than the DT and CSC. I mean, they are combined, but depending on its capabilities, more
the timing response of the detector is much faster. That's right.
You have almost completed.
Yeah, it's, there are some physics regions where I just, if you remember, I showed you like yes.
Yeah.
I just showed you like GE11 and GE21, they're already in place, and ME0
data now in run 3. Sorry. Sure.
We had actually earlier like muons and the calorimeter hits in the trigger. Now we are using particle flow as a new algorithm. So most of the detector information will be there. There are some physics regions you can see in the round 2 how the BS2 mu and B02 mu looks like, and in the phase 2 with a detector upgrade how they are separated. It gives a lot of good control over our physics output. So I want to summarize it. So we have been working very successfully in the last more than a decade of data taking, and we are participating both in physics analysis as well as hardware. There are also plenty of software. I did not mention plenty of software activity, and specifically the detector technology is very challenging now. We are participating 4 of them. And next few years, we'll have really productive data, and we'll just see how the physics comes out. Thank you.
Thanks, Sanjay, for the detailed talk, and the floor is open for questions.
Yeah.
Yes, the BS and BD to mu mu recent result is very impressive. I'm wondering how that sensitivity will continue in run 3 with the increased pileup. Will it scale with increased luminosity, or will it
well, that's with I think it's a 3 atoband data, I guess. That's how it will look like. You are mentioning how it would look.
I'm wondering about run 3 initially.
Just run 3, I think this is 3 atoband, but I think yeah, let's see, this is round 2, and I don't think I have full round 3 results yet. Yeah, I cannot quantitatively comment like how much it would improve.
Okay.
Except all I'm saying is basically the detector upgrade is going to give you better handle on the BS and B0 separation. That is, but exactly how many, I think probably you are asking on the B0 significance probably, because BS is already observed how much you can go to the B0. Yeah, yeah. We just hope we can see the B0 with 5 sigma. Yeah, yeah.
Amol?
So you of course showed the Indian institutions which are working on making hardware for the upgrade. Are there any industries that are playing a big role in this?
Yeah, so there is a specifically electronics. There are Bangalore has Micropack and Peninsula. They are actually working in the electronics, and the institutes like there are like IIT Madras and other institutes. They are producing the mechanical components with their engineering department. So that's what we are.
So say what fraction of the hardware upgrade part happens in the labs of our institutions, including IITs?
You mean assembly? Assembly, everything happens. But
what,
for example, if you look
manufactured in some Indian industry, which,
yeah, so
I can add.
it's very.
Maybe I can add a few words.
You have to go one by one, and I can explain you in one by one detector where the industry gets, where the outside goes one by one. But we do have, for example, the tracking detector. The sensors cost a huge amount of money. Only one company, that's Hamamatsu in Japan, they qualified to produce it actually, and they have to produce. They have to give it to everybody in CMS. But there are some small components that I showed you, like explored a view. They can be built within India, and yeah, some of the electronics also we are actually doing it within India.
Yeah, like for this
But not
GEM detector, some of these large scale
the foils.
they were made by the Micropack in Bangalore, and those were quality control testing and assembly were done in the institute lab. So basically, some technology transfer took place.
They are all Micropack foils, but eventually, I don't think eventually because of the lack of because of the delay in the funding, probably they will not be able to provide. Yeah, Tuhin. Yeah.
Said many institutes are participating in it.
Yeah.
So can I ask, like globally, like compared to the full effort of world's effort in putting the EGCAL together, where we are? I mean, how much are we actually?
What fraction we are contributing?
Yeah. And what part specifically that we are contributing? That
we are contributing electronics. There was a plan for the doing the module assembly, whole module assembly that you see there, whole module assembly. Still, we are trying our best to do it. But I think if Gagan wants to comment something, but mostly we are just approved to do the electronics right now. But what fraction exactly out of the total EGCAL community? If you can comment.
Yeah. So if we, I mean, as far as the technical know-how and the competence is concerned, we are there. We have already shown in the so-called mock-up module, but I think it's the funding is where we are discussing with Sanjay. So if we are on the game, we will be building 5,000 module. The total number is 25. So it's 20%. I mean, yeah, so that is the number.
One good example is when some of the optical sensors for the calorimeter were replaced, hadron calorimeter were replaced. So we contributed some crucial components in the electronics from India. Silicon, they were replaced by silicon, these photomultiplier tubes. Those calibration and their control boxes were made by the Indian groups, designed and made both.
It's in Punjab. If there are no more questions, let's thank Sanjay.
In the end, we want to grow also. If any institute want to participate, we welcome them actually to our groups. Thank you.
Thank you, Sanjay. And Avan, hear about the Bell India Corporation.
Hello. Yeah, I think I will. Yes. Yeah, all right. Okay, so it's always good to follow one friend and to be followed up by another friend. So I will talk about the next 20 to 25 minutes about the Indian contribution at Bell 2. And so just to introduce, so this is the sort of the silver jubilee of India's participation with Bell and Bell 2. As you know that Bell officially approved in 1994 and India joined in 1998. So that is the stage we didn't have any opportunity to participate in any detector hardware. And this is the famous CP violation measurement and the subsequent Nobel Prize to Kobayashi and Masukawa. 2010 is when Bell stopped taking data, but then, sort of given the quality and the volume of the data, where there has been still physics result coming out of it. As far as the Bell 2, Bell 2 was officially approved in 2010, and India became a member of SPD Layer 4 project. That I will have some slide on that. And SPD has been successfully installed to Bell 2 in 2018, and since 2019, we have been taking the data. Okay, so who are we? So this is the sort of the political map, and you can see that the collaboration is spread throughout India, maybe a little bit more concentrated towards the northern part. Probably this is outlier here, and there is on the side, and not to forget on the eastern side. So there are 12 physicists from 10 Indian institutions, and there is one more participant, interest from NIT Jalandhar. The size of India-Bell collaboration is 63, including engineer and technician, and we are the 6th largest collaborating nation. So if you want to miss the next few slides, you can just look at the executive summary. So the key point of the India-Bell collaboration has been the human research development. So we have produced about 27 PhD students, and 21 are working, and 5 of these students and postdoc, they are back in faculty. And in fact, the previous speaker, I mean, he's not one of them, and he was one of the Bell alumni. We have trained a good number of this undergraduate, master, and project student, and about 10 engineer and technicians that are involved with the detector building. Close to 50 high impact publications with the Indian leader third that has come out of this Bell and Bell 2. We have given talk at various high profile conferences. The key hardware contribution, we have been involved in the design, prototyping, and construction of so-called the SVD, which is a key component for the science deliverable of Bell 2. We have a modest contribution to the Bell 2 computing, and the part, as I said, we are, if you see 63 in a collaboration of 1,000, the leadership position that we have been held in both the collaboration has been significantly larger compared to the size of the collaboration. So here is the canvas of the physics topic. In general, we have been worked on, starting from CK metrology, CP violation, and rare decays. On the charm side, we are also involved in the spectroscopy, rare tau lepton decays, and also the physics performance studies. We hold this so-called annual Bell analysis workshop that has played a key role in sort of germinating and bringing the collaboration together. So here I start with a standard model candle. And in Indian culture, I mean, we always call Ganpati. So this is so-called the angle phi3 or gamma. It's already shown in the previous yesterday by Diego. So this is theoretically clean. You're talking of a theoretical uncertainty of 10 to the power -7. And the single most precise value comes from our friendly competitor from LSCB. That's the sort of about 4 degree. And here is the result. You can see the combined sort of result coming from the gamma. So 65 plus minus 4. So here we have the first measurement. This is the first measurement, including the Bell data with more improved analysis technique. And the fact is, we have the improved technique available from Bell 2 that has been sort of percolated to the analysis. And here we do this so-called model independent Dali's plot analysis. I mean, you know, that there is this so-called model dependent Dali's plot analysis, but there the problem is you get a sort of irreducible model dependent uncertainty, which you don't, this method is much better on that way. Of course, the statistics is the issue here. So here we take both the B2 d pi and B2 dh and the d going to k sort hh, both for k pi, k and the pi and more. And here you see the projection of the, this is on the top on the Bell data using 711 inverse femtobarn, and this is 128 inverse femtobarn. In the projection, this is so-called the energy difference. For the signal, you are expecting to be peak around 0. Since we simultaneously consider both pi and k on, so you see a peak also, I mean 0 for the right mass hypothesis and on the positive side for the wrong mass hypothesis. And the other thing you can see that here, although Bell 2 has significantly lower data, smaller data compared to Bell, it's very competitive. I mean, if you see the total scale. So we obtain phi3. I mean, this is a kind of rivalry between, it used to be between Bell and Babbage, like phi3 or gamma. But anyway, I think both are one and the same. So here the uncertainty is mostly dominated by the statistics, 11 degree. And we expect an LSCB-like precision with 10 order inverse of data. So we have to wait for a while, but of course, the work will continue. What? You're talking of this? Yeah, so this is just to, so, you know, so you can see if you draw a line here, so this is the Dali's plot projection of the D2 k sort pi pi or k sort kk in this case. If you draw a line over here and you see folding on both sides is symmetric, and this is done what we call the optimal binning. You want to get the best sensitivity to your phi3, and that's the kind of the bin you get. So 8 bin you have in the D2 k pi pi, and yeah, so this has been done in a very judicious manner. So here you see this, so what we call the Z graph or temperature graph, that essentially says the color code tells you which bin you are talking about. So so you're saying there is a discontinuity across the, well, it is done in a bin wise. So obviously you have an event either belong to this bin or that bin. So it's not like, I don't know, like what exactly you are trying to say, that continuity and discontinuity. Yeah. Yes, which is this one. Right. So the two.
No, it's treated together. These are bins in which the strong phases have approximately constant values.
Yeah,
so all the events in the black regions are treated together. All the events in the whatever purple region are treated together, et cetera, et cetera. Does this answer the question?
Okay. So now I move on to the second part. This is about the time-dependent CP violation. So here the key parameter to carry out this measurement. So first of all, we are sort of asymmetric collider pretty much at the epsilon 4s, and there is this quantum entanglement basically, once you tag the B0 or B0 bar at one point, at that particular point, the other guy has to be the antiparticle of that. And sort of we measure this so-called the delta Z. And once you know the gamma beta, the Lorentz boost factor, from that you can calculate the delta T basically. And the delta Z precision is something like, because we have now this slightly reduced boost. So therefore, in order to compensate for that, you need a better precision. And thanks to the pixel detector we have, and also 5-layer of strip detector we get. And obviously this new nanobeam scheme that also helped. So there is one challenging example in which Indian group is involved. So this is a time-dependent CP study where you are talking of B to K sort pi 0. Now, if you look at this cartoon, so what you have a neutral particle coming in and decaying to 2 neutral particles. This K sort, the other thing is K sort has, it fly certain distance before decaying to charged pion, and this is obviously a neutral pi 0. So, basically from where does this 2 pion coming from? And thanks to the beam spot constraint, we can do a pretty good job. And then you can constrain, you can form a IP tube, sort of technical detail. I don't want to get into that, but it's really challenging measurement. And why it is important, in the standard model, you expect the direct CP asymmetry to be 0, and the so-called the mixing induced CP asymmetry that should be consistent of sin 2 beta. And Gronau has proposed this so-called isospin sum rule. So you can use this as a litmus test of new physics, that if you look at this particular relation, which is supposed to be 0, in that you measure the different branching fraction and the CP asymmetry of the different B to K pi decay mode. And this particular, all other inputs are very precisely measured. And the one where we are really lacking and need to improve is so-called the direct CP asymmetry for K0 pi 0. Right. So here we have a preliminary result. Sort of first of all, in order to validate this kind of challenging decay channel, we use B0 to Z psi K sort, and to mimic your signal, you do not vortex the 2 muon coming from a single point, so that it becomes almost like a Z psi proxy for the pi 0 and then the K sort. So that we do to calibrate the signal delta receipt. So since we don't have enough statistics in hand to get a sort of reasonable or sort of a measurement, we fix the SCP to the world average value, and this is the measurement we get right now. Sort of it's not very competitive, but with a small data set of 190 inverse 21, that is the thing, and the work is going on to go for the full what we call the pre-long shutdown data for the publication. Okay, so here is one or a couple of slide I have. This is so-called the famous flavor anomalies. I don't have to really tell this thing that this observable RK or RK star, they are theoretically pristine. One is talking of an accuracy of something like 10 to the power minus 2. And that's the lepton flavor universality. But then you can have lepto quark, or you can have Z prime, and that can affect the observable, this kind of observable. And in these two plot, you see a summary of the measurement from LSCP. Obviously, is the showing the clear evidence of lepton flavor universality violation at the level of 3.1 sigma in the K star. Sorry, RK, I'm sorry. And also here in the RK star. And then we have measurement from Bell, but obviously with a larger error bar, and this was the measurement from Babar. Okay, so so right now we don't have that kind of sort of statistical advantage, competitiveness to, let's say, sort of compete with LSCP. But the point that what Diego mentioned yesterday, that the beauty of Bell2 in this context is that we have got similar sensitivity both for the electron and the muon channel. Just to sort of repeat what he said, you compare the resolution that you achieve. First of all, you look at the x-axis range in both the case, and you see the resolution in both pion and kaon and the background level, and you compare what LSCP has got. But despite the fact that the challenging fact of the electron, getting such a commutative measurement is really, really nice to see. So So where do we stand right now? So we had a preliminary measurement. Well, it's not really measurement in that sense from B to KLL, but that was a tiny set of data, but the work is going on with the full data set. We also had some measurement related to B to K star LL, where we found both the precision for the electron and muon mode are similar. There is slight, electron mode was slightly on the higher side, but that is, we want to see with larger statistics. Excuse me. So what does the future hold in this particular measurement? Here you see with 700 @1 inverse of 0.71 @1 inverse of data, this was the Bell result, whatever has been achieved. And in Bell 2, to get a sort of 10% accuracy, you need 5 @1 inverse of data. And if you look at the luminosity projection, the base or sort of the target things, we're talking of something like 26. But I guess if we are somewhere 25, when you have at least 3 or something like that, we can, although we don't get that kind of precise thing what LSCB has got, but one would like to see which way the things is moving. This is something, a kind of byproduct of the measurement that was done by the IIT Hyderabad group, but it's a very interesting measurement. Here you are assuming, so this is so-called the ratio of F plus minus to F00, which is nothing but the decay rate ratio of the epsilon 4s going to charged B meson pair or the neutral B meson pair. Assuming isospin symmetry, you can express like that. So this is the signal yield and the epsilon is the efficiency. So in order to measure that, Bell has used its full data statistics and performing this so-called 2-dimensional fit. This is so-called the beam energy constant mass, which should pick around the B mass for the signal, and the background is combinatorial. And delta E I have already introduced. For signal, it should pick around 0. And you see very nice signal. And so we determine independently for the muon channel, electron channel, and average of that. So these results are consistent with PDG and the most precise to date. And the other advantage is we have done a pretty good job to take care of the systematics due to the isospin symmetry assumption, based on which you get to this expression. So that's the most dominant systematics. So I think this is an open invitation to our theory colleague to see how best we can work on this. So I move on to the CERN decay. So here I start with something which is like, I can say fairly, it will be very difficult. I cannot say impossible, but difficult for LSCB. So this is D0 going to 2 neutral pion. And here we made a measurement of the CP asymmetry, where the flavor of the D0 is determined by the charge of the slow pion that is coming from the D star decay. So here, if you have CP violation, the two height of the two signal modes should be same. Different, and you see they're kind of same, and that is reflected in the measurement we have. So up to precision of 0.6%. This is consistent clearly with no CP violation, but an order of magnitude improvement over the existing result that we had. There is another measurement done by the IIT Bhubaneswar and Aizer Mohali group, looking for CP violation and branching fraction in D0 to K sort. This is again 2 neutral kaon. I mean, this is somewhat bit, I mean, this obviously LSCB can do, but the challenge here, because the K sort flies certain distance before decaying. So here, this used to be the most sensitive measurement of CP asymmetry, and this was, this plot was a old plot, and this was the LSCB RON1 result. But after kind of quite a few trials, they have very recently come up with the result, which has bet the Bell uncertainty, so about 1.2. Our uncertainty was 1.5%. So this is close to the theory limit given here. In terms of the branching fraction, this is the most precise measurement, and there is work is underway from one of the Indian group to look for this D0 to K sort. Okay, so this is very quickly about D0 to gamma. Again, a nice channel to search for BSM physics. And what you see, this is mostly the background, the peak you are seeing. This is obviously not the signal. this is a peak coming from D0 to pi0, and one of the photon either they're not reconstructed or somehow passing through the crack in the detector. So here we put the world's best limit of 8 × 10⁻⁷, and in this plot over here, you see this is the standard model prediction taking the long distance effect into account. So it's 10 to the -8, and there's some incarnation of supersymmetry MSSM says this was the kind of range, and with the upper limit that we have set, we are kind of sort of restricting that part. So Punjab group is working on for this measurement with the full belt, with whatever belt to data we have, and they have already done the identification of the control sample D0 to K sub pi0. Okay, so this one very quickly about this X3872. Some of you would be knowing that this is the most highly in terms of citation, this is the sort of 2000+ citation and the highly cited paper from Bell is even more cited than the CP evaluation observation paper. So here the JPC determination from LSCB clearly says it's 1++, and that says it could be a charmonium-like particle. But then if it's CIC1, then the single pionic transition should be suppressed. But Bestri has observed that in this particular case, they see a pretty good, the ratio is 0.88. So this rate is much larger than expected for charmonium. For example, psi prime, you see the number is 10 to the -3. So motivated by this in Bell, we have searched for this decay. And as you see in this projection here in so-called invariant mass of CIC1 pi0, we don't see, sort of no signal. This is where the signal should come. And this is another exotic particle, X3915, where we see about 2 to 2.3 sigma. And so therefore we put upper limit, although our result does not contradict Bestri result. Okay, so just, yes, I have 2 more slides. So this is what I call the provocative statement building the heart of Bell 2. So Indian institutions are involved in the design and prototyping and building of this so-called silicon vortex detector. So there are 5 layer, 4 layer of what I'm saying, layer 3, layer 4, layer 5, yes, 4 layer and 6 layer is what I say, including the pixel. And this is important for the vortexing. Vortexing is crucial for the CP evaluation measurement and charge particle tracking. And we had morning discussion with Tuhin and others that how you can have the SPD only tracking for low momentum. And the other thing that we have shown also that it can also use for identification, the particle identification, especially for low momentum. So this is a kind of a real photograph of a detector, which was built by an Indian team. And just proud to say that this detector is able to measure the charge particle position to an accuracy of 15 to 20 micron. Okay, so since Amol was asking that question, so this is successful R&D with Bharat Electronics Limited, pretty close by here, in developing AC coupled single-sided silicon microscope sensor. This was done keeping in Bell 2 upgrade in mind, but as you could imagine, for a low energy experiment such as Bell 2, the material budget is a key criteria, and so therefore single-sided. We have to go to double-sided, and then there are a few other issues. But the fact is we have been successful single-sided. This can be useful for some homegrown experiment, for example, nuclear physics or other experiment, or even some satellite-based experiment where material budget is not such an issue. Okay, so here, this is the penultimate slide, just to show that how the Indian group is also involved with the charge PID identification. So this is a other than the vortexing, this is the second most crucial factor for the success of any flavor experiment. And here our colleagues, they have been working on determining the particle identification performance for charge pion and kaon using this particular decay. So this decay is very important and very nice because you don't have to really identify, you use any PID thing just from the charge. As soon as you know the slope pion charge, that tells you the same charge particle that is also a pion, and the opposite one has to be kaon. So kinematically you identify the particle, and then you can look at the PID information. And this is the kind of state-of-the-art measurement we have based on a likelihood-based hypothesis. People are working on also using the machine learning. So the current result is 87.3% KNRID efficiency with a fake rate of about 7.8% pion. That is in data, and this is the number with simulation. And so this is something I thought, since I said SVD can SVD help, and indeed SVD can help for low momentum region less than equal to 1 GeV, and that is clearly shown in the data. And this paper is already, this is part of a SVD paper which has already been accepted in Journal of Instrumentation. Okay, so that brings me to the summary, where I want to say the plans for Bell 2. Basically, the most crucial deliverable from the collaboration is the high quality PhD that we have produced or will continue to produce. The students are really working on the thrust areas of flavor physics. Whatever you name it, we have someone or other working on that. And there are also students are working on the operation and maintenance. Little bit of interest we have. Many of us are overly subscribed on multiple projects, and the thing, but on such some small scale, we are involved with some upgrade software side. For the PID particularly, this machine learning technique will help, and work is undergoing on that. Now that SVD is successfully built and delivered, we are working on to take care of this SVD, particularly during the COVID pandemic. Students took shift, operational monitoring shift, sitting in India, yeah, I think this is the last thing I don't have to say that. Thank you.
Thank you, Gagan. Floor is open for questions.
I had two questions. One is on the SVD slide. I just wanted to get an idea of the physical size of SVD. There was no human being
Size of the
size.
Okay. Yeah, I should put the protractor. So this is like the layer 3. Jim, sorry, what is the number?
Approximate size.
I'm just forgetting that. Sorry, I'll give the number. Like I have it, but
no, this much. There's no human being standing there.
Oh no, you're talking of this one.
Yeah.
Oh, this one.
This much. The second.
I thought you were saying where they're in the Bell 2. Like what is?
No, I wanted to look at understand the physical scale of this object that you have in the photo.
These are sort of 4-inch. Yeah, so you have 3 modules. So there is 3 sensors. One here, and for this the middle one is where we use so-called the origami concept, and then there is a trapezoidal one. So you can see sort of corner to corner. That's the dia of what we're saying. Okay, there's a little bit of, yeah, this week.
And the second
I will give you the number. Sorry.
That was all I wanted. Yeah. The second was yesterday there was this talk by Sabyasachi, I think. He talked about B going to Ka and axion going to 3 pions.
Yes.
You think something like that is possible to be done at Bell 2?
Yeah, as far as I know, there is some work is going on, but not anyone from Indian side working on that. But yes, it is very interesting. B to Ka, you are saying, right?
A and A goes to 3 pions.
Yes. So the advantage will be like as you go to the multi-body decay, so you'll have the low momentum track on an average, and so with the Bell 2 detector compared to, let's say, in the Bell data, we will have a much better competitiveness there. Yeah, it is possible.
Any more questions to Gagan?
So this is like a question regarding the timeline of the Bell 2 program and what lies beyond that. So you had an arrow hitting the 2018 Bell 2, but then what after that?
Which arrow you're talking of? This one?
Towards the beginning of the talk, like you saw the timeline.
Yeah. Right. So right now, as you know that the goal is to accumulate 50 atomic inverse of data, and with the this is a machine where you are looking really. I think the real challenge here, not from the experimental side, the real challenge here from the accelerator side. You are pinching the electron and the positron beam to the level of nanometer. Okay, and at that level, there's lots of challenge our accelerator colleague are finding. So therefore, you see that the way we want to achieve the peak luminosity is not an easy task, not an easy task. So the current projection to get the 50/1 inverse is you're talking of something like 2030 to 33, something of that order. And that's, you know, the timeline you are talking of. But even if the Bell to stop taking data during that, I mean, around the mid 30, let's say, but there will be people are already
L3 in the pipeline.
Yeah, so there is, well, there is some talk going on at some level, but you know, there is a connection to whether Japan will host International Linear Collider. I mean, this probably goes to the, I mean, it may be a little bit difficult for Japan to have both ILC and Bell-3 to be fair enough. But if ILC doesn't come in Japan, then I would say, I mean, this is what I'm saying outside. I mean, you can take it a little with pinch of. So the Bell-3 definitely is something people are, the Japanese community and the broader community are very much interested, particularly in connection to LSCB. I mean, given the synergy and the complementary environment.
So how about B2 K-tau in your priority list?
Oh yes, that is very much in the priority list, and already we will have one in Bell data itself. We will have we're just going you know, the collaboration wide review is going on, but we will have from both Bell and Bell-2. See, I said for the muon and electron, you are talking of 5/1 inverse of data, but K-tau or K-star tau, this is something we can do. You know, obviously we can improve on the limit and then see, but yeah, this is very much on the priority list.
So even better than LHCb?
Yes, of course. I mean, with the multiple neutrino and the thanks to the, you know, you have basically 2B and nothing else. And in LSCB, they profit from the high longitudinal boost and the dipole detector. So that's what they do. But in our case, it's significantly, we should have better sensitivity.
I don't see any more hands raised. So let's thank Gagan, and we hear about future E+ E- colliders from Professor Wilkinson.
Yeah. Okay, thank you for this invitation to speak about future high-energy positron colliders. So I'll spend a few words, not many I concede, on the physics motivation, but then I'll consider the two options in front of us, which are linear and circular. A couple of slides on the ILC, one slide on CEPC, and then I confess I am an advocate of FCC EE, and this will be the main focus of my talk. Okay, so a future E+ E- collider is here taken to be a machine that will enable high precision Higgs studies. We've just seen all the wonderful things that lower energy E+ E- machines can do, and these machines will continue. And indeed, there's plans for future such machines like the Super Tau Charm Factory. But I'm concerned with machines which will operate for Higgs studies at the Z pole and higher energies up to a TeV or so. So I apologize for not including many sort of reasons why it is acknowledged that this is a priority in high energy physics. My talk is rather short, but taking this as read, for instance, this was a conclusion of the recent European strategy update. There are two broad options under consideration, linear and circular. They have different strengths. For instance, in terms of luminosity, linear machines give you the best value for money above 350 GeV or so, but below that, a synchrotron is your best bet. Talking about polarization, longitudinal polarization is quite easy to achieve for linear machines, and this is valuable for physics studies. But synchrotrons have this fantastic attribute that they naturally have transverse polarization, and this is absolutely vital for energy calibration. And another advantage of the circular machine is that you have multiple interaction points, so you can put several experiments there concurrently. So until about 5 years ago, or maybe a bit before, the linear machine was clearly the front runner. So historically, that made sense. The Higgs could have been rather heavy, and of course, the LHC was expected to discover many high mass SUSY modes that would require detailed study. And unfortunately, we know how that has worked out. But let us therefore talk about the front-running linear machine, the International Linear Collider. So in its current incarnation, this has a center of mass energy of 250 GeV, a luminosity of 10 to the 34, and a length of 20 kilometers. No, it relies on 8,000 superconducting cavities. So if you were to operate this machine over several years, this is essentially what you would do. You would start at this energy of 250 GeV, accumulating data, essentially HZ data for Higgs physics to look at Higgs couplings. You would upgrade the luminosity of the machine to increase these data samples. You would then upgrade the energy, which would mean making the machine longer to 500 GeV, where you produce Higgs from WW fusion. And you would also make a dedicated run to study the top mass. And if you wished, you could do a run at the Z pole, or you could raise the energy still higher if you extend the machine still more to a TeV or so. The actual design for the machine is very mature, and also the detector studies are also. There are very detailed designs for these two detectors. There's only one interaction point, but there's this rather ambitious scheme that you would have push-pull operations, so you collect data over time with both experiments. So this has been around for some time, and a huge amount of work has been invested in ILC studies over many years. For instance, the TDR dates back to 2013, already quite some time ago. At that point, the baseline was 500 GeV. And since then, we have been waiting. We've been waiting for approval. And particularly for the proponents, the situation's rather reminiscent of that of the two tramps in Beckett's play, Waiting for Godot. They wait and they come back tomorrow, and then they will come back the day after tomorrow. And maybe the question we should be asking is, perhaps we should wait no longer. Before finishing the discussion about linear machines, we should acknowledge there are other plans on the table. There's a so-called CERN Plan B, which is CLIC, based on a very novel technology, and this could take you up to really quite high energies. But this is a project with quite a long time scale. And very recently, ideas have come from the US about things that could conceivably be done at Fermilab based on new RF technologies. But I really would say that these come with a word of caution, because there's a very long R&D road ahead. Let me then therefore introduce the FCC, the so-called FCC integrated project at CERN. So taken from the top of the Jura in winter, here is the LHC, and the FCC tunnel would be a tunnel of between 90 and 100 kilometers, stretching over the Genevois plain behind the Salève and coming back again. This would first house a FCCEE, a high luminosity plus E minus collider. And then eventually you'd install in this tunnel a hadron collider, which could go up to energies of 100 TeV or so. Conceptual design reports were published in 2019. And then in the recent European strategy update, both the HH machine and the E+ E- machines in general were given very strong encouragement and high priority. And now the FCC is undergoing a 5-year feasibility study, which will conclude in 2025. Before telling you more about that, we should concede that there's another circular machine under consideration, the CEPC in China. The main characteristics closely resemble those of FCCEE. If you look at the CDR, they were, it was probably less ambitious in design, but the years since then, it's evolved to something which is quite close to the FCCEE design. Here's some information on, possible timelines. Essentially, the bottom line is if you believe everything you're told, this could actually come into operation 10 years before FCCEE. That means the mid-2030s. But there are many uncertainties, and I would regard this as very ambitious and aggressive. But certainly we should watch closely. Now back to FCC, and let's now consider the various running points, the luminosities against center of mass energies. And I just want to give you a few words about the physics we could do with each of them. The first thing you note is the luminosity. So FCC is here in black, going from the Z pole up to about 365 GeV. The Higgs studies start here at 240 GeV. These luminosities are enormous. They go up to over 10 to the 36. And you note that even at the way you do the Higgs physics, you're substantially above where the ILC will be. It's delivering many, many more Higgs per second. So how do you achieve these luminosities? This isn't a accelerator talk, so all I'll say is that one is leveraging all the experience, not only of LEP, but of all E+ E- machines since. In particular, the machines of the B factories with their double ring operation and their top-up injection. So getting to the luminosities I'm talking about is, it will be difficult, but it is certainly not science fiction. This is in some sense tried and tested technology. Okay, so taking energy points one by one, let's start at the Z. The idea here would be to take over 4 years, 150 inverse attobars. That corresponds to 5 times 10 to the 12 Zs. It's something like an order of 10 to the 5 above that which was achieved at LEP. It's enormous. This project, therefore, is sometimes called Terra Z or Terra Z. So why do you want to do this? LEP's been done before. Why go back? Well, now we've discovered the Higgs and that standard model is complete. And the emphasis is more and more on making precise stress tests of the self-consistency of the theory. And one can imagine with these data, you can make measurements of the parameters which were made at LEP, which we all know are very, very important, with in principle a precision which is 500 times better. Nowhere else, anywhere in particle physics, is there the possibility of making such a huge step forward in sensitivity. So to look at the line shape, for instance, okay, so we're getting so much data. Do you really need that data? Do you really need 4 years of operation? Or the lesson from LEP is, yes, you do. Making line shape scans is a really delicate business. It's not a year-one measurement. And so we need to devote time to this. And certain systematics certainly require particular attention. Let me just pick out one, and that's the knowledge of the collision energy, which is absolutely essential here. So these were the collision, these were the uncertainties from that source, which were the dominating systematic on the Z mass and the Z width at LEP. And the statistical uncertainties FCCE will be a 4 kV and 4 kV. So compare that with the MEVs here. So this does not look easy at all. So let's remind ourselves how actually we measure the beam energy here. And that's through this miracle of resonant depolarization. So in the synchrotron, the beams are transverse polarized, and the precession frequency of the beams is proportional to the beam energy. Now, this gives you an instantaneous measurement, which is super precise, down to a few, at the keV level. At LEP, however, resonant depolarization could only be performed in a few fills before and after the collisions. And this is where the problem lay. You've got very good instantaneous measurements, but you then had to track between these measurements. And understanding how things evolved was very, very problematic. One had these effects such as the earth tides, which distort the ring and pull the trajectory off center in the quadrupoles. These giving distortions of 10 MeV at LEP, and they would be an order of magnitude larger at FCCE. Longer term distortions by the water level in Lac Le Mans, issues such as the magnets rising due to stimulation on the beam pipe from currents from returning trains. All of these were issues. So how can one hope to actually control things to the level we wish at FCCE? Well, at this machine, in contrast to LEP, the idea of actually doing energy calibration is built in right from the start. And the key idea is, rather than making very measurements of resonant depolarization scattered by weeks at a time, we would do it continuously. We will essentially measure the energy of the beams continually on non-colliding pilot bunches several times an hour. And this removes the first order, all the problems we had at LEP. We can also change the RF frequency continually to keep the beams centered in the quadrupoles to actually remove these residual tide effects. So with this approach, and with many other issues which we can't go into here, there is confidence that the collision energy systematics can be limited at least to 100 kV on MZ and 20 kV on gamma Z. This is still somewhat above the statistical precision, but the expectation is that an even better performance will be possible. Work is in progress. And if you turn to other observables where the actual experimental systematics are much more tractable, for instance, forward-backward asymmetry for muons, tau polarization, forward-backward asymmetry for B productions, all very, very important observables. Here, the hope is that you could really extract the full power from the statistics that you get from these 4 years. And then with these data at the Z, there's other things. You can do flavor physics, all this wonderful stuff that's being discussed. You get a B sample that would be 15 times larger than Bell 2 ultimately hopes to collect, and a sample highly complementary to the LHCb upgrades. There was a discussion about B to K star tau tau just now. This is obviously a simulated version of the signal one would hope to get at FCCE. And this is something which is unique to this machine. We won't have it at LHCb, and statistically it lies beyond Bell 2. Similarly with tau physics, if you want to study lepton flavor violating tau decays, this machine will do it much, much better. And even direct searches, even looking for new particles at the Z, you can do that, for instance, looking for heavy neutral leptons, axion-like particles, lepton flavor violating Z decays. With 5 times 10 to the 12 Z zeros, you get very, very powerful constraints, or hopefully discoveries. But we need to move on. Let's talk about this energy, the WW threshold, and also at the same time, the TT bar threshold. Okay, the idea here is to measure the mass of the W and the mass of the top. So for the WW, the idea would be to take a threshold scan. This was done at LEP, but with rather low statistics. With this, and maybe with direct reconstruction, it will be possible to measure the W mass at this machine a factor 20 better than we know it today. This was always known to be an important measurement, but this has really been highlighted by this anomalous result from CDF. Okay, so to make a really precise W mass measurement, we really need to go to an electron-positron machine, and this is the place to do it. One of the reasons you want to do that is to perform these closure tests of the standard model, these famous plots of MW against M top, where you compare the direct measurements with the indirect predictions. So we will improve both the mass of the measurement of MW, M top, as I will show you, and also the indirect predictions. In fact, the indirect predictions have limitations here, which would become crippling at FCCE, but all of these parametric contributions to the error, we will actually be able to measure better at this machine, including things like fine structure constant at the Z pole. And I can say more about that if you're interested. So the top mass will also be measured similarly in one of these threshold scans. This at obviously 365 or 350 GeV. And then if you put everything together, this is a rather ugly plot, but it's the same closure plot you saw before. In blue, this is the current prediction. In green, this is the current set of measurements. Down here is where you expect to be after FCCEE. So in red, the predictions we will have then, and in blue, the measurements we will have then. And you see the exquisite exactitude of the situation that we will hopefully achieve. And of course, we now need to talk about the Higgs. So Higgs physics will take place at there's two key energies. The first, where you produce the Higgs together with the Z, that will be 5 inverse attobars taken over probably 3 years. That will be 10 to the 6 events. And then at this higher energy, I will say a little bit more about that. That is WW fusion. Indeed, here you actually see the two processes. One sees the cross sections against the center of mass energy, and you see, here the HZ dominates. Here you're getting more contribution from the WW, the Higgs fusion, and these are very complementary. This brings you very useful additional information. So this is one of these publicity tables which show you the precision on Higgs coupling for a variety of machines. All one needs to seek the take-home message is that you do very well from combining these two energies, that the general precision you get is better than 1%. This is very, very valuable indeed. And combining with what we know from, or we will know from the high luminosity LHC, we will know much, much more about the Higgs then than we do now. There's much more I'd like to say about Higgs, and I won't. There's no time. Ask me afterwards or look in the backups. I'd like to say some words about Higgs self-coupling measurements, and something which is very, very tantalizing, very interesting, the possibility of measuring the Higgs-Yukawa electron coupling. Possibility of, this tiny constant at FCCE, this is tantalizingly just or possibly just out of reach. But I say no more. Okay, so where are we? What's the status? What's the status with the experiments, the detectors? So you might say, well, compared to the FCC, compared to the high luminosity LHC, the detector challenges are really rather modest. As radiation is not an issue, event rates will be high, but not as high as at the HL-LHC. This is true, but on the other hand, there's the precision we are striving for is unprecedented, and this is driven by the event samples we'll get at the Z. I mean, in contrast, I'd say the Higgs physics will be easy. We'll need to monitor and have stability of detectors and operation and resolution at the 10 to the -4 level for luminosity, 10 to the -5. This is a real challenge. So there are already 3 candidate experiment designs that have emerged. This is actually evolved from something which was originally designed for CLIC. This is essentially silicon-based. This detector here has a very lightweight drift chamber in the middle. This is a new concept which is based on a Nobel liquid calorimeter. But I should emphasize that these are not set in stone, and there's plenty of room for new ideas, optimization, etc., etc. And the current, if you go to the CDR, you will see a design for FCC which has 2 interaction points. I think that we will not remain with this. I think we will end up with 4. There's many advantages with having 4. Not least, you would have a opportunity for many more diverse detector designs to pinpoint different areas of physics. You see here, there's no detector which is optimal for flavor physics with a dedicated PID and a crystal calorimeter, for example. So this is an area where involvement would be very welcome. Coming back to the general timeline, there's this feasibility study underway that started in 2021. Middle of next year, there will be a midterm review and it will report at the end of 2025. So this is, you know, the clues in the title. It's a feasibility study, really trying to understand whether this project is, in terms of the civil engineering, in terms of the accelerator, in terms of the financing, whether this is you know, something that can be done. Just to give one, you know, one minor example, you know, a lot of effort is going into actually designing, you know, planning the exact ring layout. I said the machine will be somewhere between 90 plus kilometers. One needs to, you know, try and plan, position it really precisely such that it goes through all these cantons and the access shafts, you know, not interfering with sort of key areas of civilization, that there's infrastructure there, etc., etc. For a while, it seemed, this was until rather recently, the actual exact circumference of the ring was going to be 91.2 kilometers, which in other units is, you know, a very good omen, because it really emphasizes, you know, one of the big physics goals of the project, which is the Z run. But I'm sorry to say that I know this is being tweaked again, and I think we'll stay within the Z mass to 2 significant figures, but not 3. Okay, so we need to talk about the timeline and the finances, and this is where things clearly get awkward. And rather than you know, make things up myself, I quote from the CERN DG. There were statements made in June of this year. So we are running at CERN the LHC, and the high luminosity LHC is approved, and that will run, you know, until the end of the 2030s. And then after that, there will need to be a breathing space before a new machine can begin operation. One would hope that this project, if approved, it would be approved before the end of this decade. So one talks about, therefore, operating FCCE from 2045 up to 2060. And the FCCHH, well, I don't even want to go there, but that would come afterwards. And that takes us towards the end of the century. The cost of the project is not cheap, but this brings you, you know, 2 accelerators with, you know, for the price of 1. Well, the tunnel does for sure, and some of the infrastructure. So FCCE, that's something like 11 million Swiss francs within these assumptions. So the funding model needs to be understood, and that is part of the feasibility study. So what are the opportunities for involvement, particularly from Indian groups? So I would say that you know, this ongoing feasibility study presents an ideal time to become involved. One could become involved in the accelerator, and I know there was a meeting in this very institute last week where many of the CERN accelerator team came, and several possibilities were identified and discussed. In terms of theory, you know, with the experimental sensitivity we're talking of, there needs to be, I mean, the theorists need to up their game. So those of you who are not working on the multiverse, I would encourage you to come and do something which would certainly be very welcomed by your experimental friends, which is to, you know, try and improve the calculations to enable us to follow through this program. And I give you here a report, a theory report from a workshop of 3 years ago. And then in terms of experiment, one can conduct case studies in selected topics. There's a whole list of these case studies which we wish to conduct. These will help us consolidate the physics case and evaluate the detector and theory needs. We want to optimize the experimental layout. So we call this the detector concept stage. Again, these experiments I showed you, these putative designs, these are just designs on paper. There's a lot of room for new thinking. And there's R&D in detector technologies. So I can give you names. I just include here one of these horrible organograms which show you the so-called physics experiments and detector pillar of the project. So in these boxes down here, and if you follow up with these names, these are people you can talk to get involved with this. And indeed, parallel to all this, there's actually, it's somewhat confusing, but there's another workshop going on, which is the so-called ECFA workshop, which is pursuing more or less exactly the same things, but in a broader context, in a context such that the efforts will be equally useful for the linear collider should that go ahead. And there was a meeting in DAISY in October. So there's a recent snapshot of this from Aidan Robson, which you can click on. Okay, so I should finish now. I really do believe that the high-energy +E- collider is the natural next step for particle physics. The ILC is certainly, in the rather infamous words of Boris Johnson, talking about a Brexit deal. It is an oven-ready project, but it's been an oven-ready project for some time. And I would say that since this became a mature project, we've thought more, and we've realized that it's, the opportunities are still greater. It's important to make high sensitivity studies, not just of the Higgs, but to take the opportunity to perform studies of exquisite precision in electroweak physics, QCD, and flavor. And FCCE is the machine that can deliver this. It's a more ambitious initiative with wider physics goals, and is also the obvious stepping stone to 100 TeV Hadron Collider. And now is the perfect time to get involved, so come and shape the project, please.
Thank you so much. Let's thank. The floor is open for questions.
Hello. Do you have any projections on the Higgs cubic and quartic couplings in this?
A little, yes. I was going to say something about this, at least, oops. This, right? So the FCCE will not run at an energy where it will, well, it does not plan to run at an energy where there will be Higgs production. Right, that's the first thing to say. I mean, that will be mapped out with the best possible precision by the FCC HH, with a precision of something like 5%. This is, this is of the utmost importance. This was mentioned earlier. What you can do at FCCE is you get indirect sensitivity to it through diagrams such as this. And so what you want to do is to measure cross sections very, very well. And if you do that and you combine with the information from the high luminosity LHC on this parameter kappa lambda, you can get precisions of something like 34%. And you can improve this by optimizing the running plan better. You could maybe take more data at this higher point. And if you go to 4 interaction points, you can do better again. So if you decide that this is something you really want to go after, then there's ways to at least indirectly measure this parameter with high significance through these indirect means at FCCE.
Yeah. So, I mean, this is exactly on this slide. You can hear me, right?
Yes, yes.
Yeah, sorry.
The thing where you were now.
Right. Okay. So, I know Leif had the example of 4 experiment, and you know very well, like there was this, one of them was more flavor ready, what you call microwave oven ready, or in which you're involved. And so don't you think 3 may be a better one, like where you have 2 general purpose like Atlas-CMS and 1 on
3. Well, yeah, my
is there something
I worked
more?
on LEP, and I always thought that yeah, LEP could have survived with 3 experiments. I won't tell you the one which I think we could have done without. However, because just the practical considerations of an E+E- machine, you have to have 2 or 4. 3's not, I mean, 3's, I mean, you have to have an interaction point. You need to have 4 interaction points or 2. So it would be stupid not to equip the 4th one.
Yes, yes. So this is not a physics question. It was a great talk. I was wondering at the beginning, you showed the scenarios. You know, we have this thing, but this has to wait until the end of LHC luminosity, and then in China maybe they can do it earlier, and then there is this ILC suspension. And, I'm wondering, is it conceivable a scenario in which some of these big efforts decide to, cooperate rather than to compete? I mean, CERN has joined forces with Fermilab on the neutrino program. I was wondering whether it's possible that, I don't know, maybe a CERN-China cooperation on just choosing one of the two projects could be on the table at some point? Because I'm afraid otherwise it will, the discussion will push this farther and farther in time.
Well, you're right on both counts. You're right that this is not a scientific question, and you're right that it will push things back if things happen like you say. I mean, I could point that there's been very warm, constructive things said, for instance, in Japan, which looks like they're trying to maybe back out of the ILC, but talking about working with other nations, with other labs on other machines. And I've seen statements made in China that they would be very willing to collaborate with CERN. So yeah, collaboration we hope is the way ahead. But no, at the moment, at least within CERN, this feasibility study is going ahead. There'll be a strategy update in 2026 or 2027. And we very much hope at that update, there will be a clear statement from the at least European community is that we want this machine. And I mean, I think it should be this machine, but it could be another one. Oh yeah, no, hey, it's a senior member of the CERN directorate who will correct me and tell me what I...
No, just a comment on, I totally agree with you, but just a comment on that question is that yes, cooperation is possible, although not always China has shown great science in that direction. But at the end, you have to decide where you want to put the machine, and you can put half on one side and half on the other side. Okay, so obviously that is the issue. And you made the example of dunes, but at CERN we're just constructing a cryostat, and that's very different. The experiment will take place at in United States, so that is a big issue, and that can never be resolved just with collaboration.
Rohini?
Actually, I have a physics question, but now I thought I will just make a comment based on this discussion, that as far as I can see, I mean, there are big uncertainties with CEPC, but to some extent, there will be some clarity rather soon if whether China actually selects it for their next 5-year plan. And those discussions are, so to say, underway now as we speak. So at least there will be some clarity whether this very aggressive 2030 target will be met or not. I mean, this is just a
I agree.
Adding, I mean, just adding something to the whole.
Thank you.
But my physics question, not question actually, maybe a question, is that now it seems, your first transparency very nicely indicated one advantage that we all used to rave about ILC, namely the use of polarization, linear polarization. But now it seems like if one can get those luminosities, then that advantage is, physics advantage is really not there anymore. Is that a correct statement?
Yes, certainly for the electroweak measurements, because you can access all information. For instance, the tau polarization and now measurement allows you to decouple things and get directly at what you would measure with left-right asymmetries with a transverse polarized with longitudinal.
It will be
very
similar to left versus SLC now.
Yes, and the actual the huge advantage in statistics you have at the Z0 just offsets anything you can do with the polarization. Yeah.
Essentially, comparisons will be SLC versus left and.
Yes, I think so. Yeah. Yeah. Oh, please.
You're saying that we will have an answer from China and that will add information. We'll add information, but I don't think it will be decisive. Whether China puts it in the 5-year plan, that's not sufficient for the community to understand if they will actually ever complete it. And take the example of the SEC LHC, right? I mean, you know, at that point, we could have said at CERN, well, stop the LHC because there's another project ongoing, and you would understand what would have been the consequences of that. So I think while CERN should continue, of course, to the discussions and be very open to understand what's happening in other places in the world, like, you know, the ILC. We've seen a lot of up and downs in the ILC. I don't think that CERN should base the decisions according to statements made elsewhere. I think CERN should go ahead with the program that they consider the most valid, and then always be open to collaboration, but not be influenced at the point of changing the program based on statements made in Japan or China or elsewhere.
No, I absolutely agree with you. I mean, I just wanted to say that, in fact, what I have a feeling that for CEPC, I mean, right now, the way I have seen the funding model that they're thinking of is where the central government gives only maybe 1/3, and the rest of it has to come from the individual state where it will be based. So there are huge uncertainties. I mean, even worse than SSC, I would say. And I just wanted to kind of say that there is, even the funding model is not very clear with them. So I basically support what you're saying, is that right now the FCCEE seems to be a project that the rest of the world at least should at least right now decide if this is the best and focus.
About the polarization, we discussed that.
Yeah. That was the science. In case that was not that.
Any further questions? I don't see hands raised. So let us thank once again, and this session is closed.